3. In this video, we're going to look at surface gravity waves computed using a finite difference model that I wrote here in MATLAB. So in this window, I have the text editor with the water waves part 1 code. I'm not going to code it live like I did in the other videos. In this one, I've pre-coded, so I'm taking the dish out of the oven and serving it to you. After we've run it and looked at the solution, we can go back and look at how the codes work. So I'll explain line by line how the finite difference model works. I think the best thing to do is to first do a simulation. So I'm going to run the model. Water waves 1 is what it's called. This is the text editor. This is the MATLAB window. And here it goes. So it's going to make a plot. And what we see on the top is a domain of depth 500 meters, 3 kilometers wide. And the blue curve at the top is the sea surface. And the little points are the trajectories of Lagrangian particles. The red dots are the position of the particles, and the trail of blue dots is where it has been since the beginning of the simulation. And the red arrow is the instantaneous velocity vector used to advect these little particles in the flow. And so the model was initialized with a single wave of wavelength 1,000 kilometers. And so there was 3 waves fitting in the domain. And I also chose the velocities to go with the sea surface height such that we have a pure monochromatic wave, one wavelength wave that is moving in the positive x direction. And I think the simulation lasts long enough for the wave to cross the basin. So that's the width of the basin divided by the phase speed for that wavelength. Alright, so the model is completed. Let's run one more time so I can point out some features of the solution. Yeah. Alright, so what you'll notice is that the little particle orbits, they reach their maximum. They get top of the orbit just as the crest is passing above, and they will have the bottom of their orbits just as the trough is passing above the particles. So you can see that little particles are executing little circles, and the particles at the surface, it's this circular motion of the particles that ends up producing this wave that propagates along the domain. You also notice that the size of the circles, they decrease exponentially as we go with depth, and that is a function, of course, of the wavelength. The longer the waves, the deeper they penetrate. If I was to initialize with a shorter wave, the orbits would decay more quickly. We can maybe try that right after. We can change the wavelength to be shorter, and you'll see that the circles will decay more quickly as a function of depth. So here the size of the orbits is pretty much 0 by the time you reach to the bottom of the ocean. So this particular wave, is not long enough to feel the bottom. So this would be an example of what's called a deep water wave. Alright, so let's clear the figure again, and let's see if we can change the wavelength. Well, maybe what we should do is go through the code first, and after we've gone through the code, then we can try to modify the code. Alright, so here is the code, how it works. At first, we set up some parameter values, the density, G for gravity. L is the horizontal extent of the basin in meters, so it's 3,000 meters or 3 kilometers. The depth is h, which is 500 meters, and we are discretizing the domain using 901 or 900 points in the x direction and 100 points in the vertical. All these parameters get packed into this array called par, or the structure, so that it's convenient to pass it in and out to other functions. Now after that, there's 2 subfunctions here, make grid and make operators. The first one will make a discrete mesh of grid points with the u, w, and pressure points that I talked about in the previous video in the lecture. And ops is going to be some finite difference operators, namely for the gradient and the divergence. And these are computed, or created I should say, using the shift operators I've talked about in previous videos. We'll go over these 2 subroutines later. Alright, so after that, we want to create an initial condition for our model. And what I've chosen is this wave of wavelength 300 times the grid separation separation. So that turns out to be 1,000 meters. So the wave here is 1,000 meters. So there's 3 waves in the 1,000 meter wide domain, or the 3,000 meter wide domain. Yeah. K is the wave number, omega the angular frequency, and it's set using the dispersion relation that we derived in class last time. C is the phase speed, A is the amplitude in meters, and so I picked this amplitude of 25 meters. I could pick any amplitude for a linear model. I chose it to be big enough so that you could actually see the size of the orbits based on the wavelengths that I had. And so it's just for cosmetic regions I picked that particular size. And T is the period of the wave. After that, here we have the part where we simulate. So down here, we start off by setting a time step, which is the period divided by 1,000 steps. So we're going to have 1,000 steps per period. T is the time, and then we initialize the state vector, or the state of the model, and that gets done with the subroutine initialize, which I'm going to show you now. But the model state is saved in here in this array time called S. So the model state consists of the sea surface height, so that's as many grid points as there are in the horizontal direction, and then followed by the u velocity at the 2D mesh of points, or the u component of the velocity, followed by the w component of the velocity over the 2D mesh. And after that, the state I've augmented with an array, I think, of 25 discrete particles that I'm going to vect around with the flow so we can trace the orbit of the particles. So the way we're going to do that is that the position of the particle is satisfies dx dt is equal to u and dz dt is equal to w. So since we're computing u and w as part of the water wave solution, we can then integrate dx dt equals to u and w, dz dt is w, to find out where the position of the particle is at all the future times. So let's look at the subroutine initialize to see how it's done. So down here, we set up the initialization, and what we set it up, let me center that, yeah. So what we do is we have a sea surface h, which is just a cosine with wave number k, where k is given by 2 pi over lambda, for lambda being 1,000 meters, and an amplitude of 25 meters. And from consistent with that sea surface height and a wave that's propagating in the x direction, we have the w and the u, and they are given by akg times sine of kxp times the hyperbolic sine and divided by omega cos, hyperbolic cosine. And then the u is almost the same thing, except what used to be a sine is a cosine, and what used to be a hyperbolic sine is a hyperbolic cosine. So this is based on the analytic solution we derived in class. So these initial values, and then I also initialize a discrete array of mesh points, not mesh points, of points positions for the Lagrangian particles. And these, I've offset these positions such that in the x direction they are at the right phase, so that they will do perfect little circles that follow the sea surface height. So I've included this little factor of sine k x naught, where x naught is the initial position, so that I shift them a little bit, the x and the z, so that the first row of particles are right on the sea surface. Now this state here, comprising of h, u, w, and these positions, are going to be stored in a big 1-column array of numbers. And so I also have to have these indices here, ix, that tells me the position of the x component of the Lagrangian particles in that big long state vector. Iz is the position, the rows in the big state vector where the z coordinates of the particles are. And I also have these up here. IH is the position in the state vector, the rows that corresponding to the sea surface height, h, the rows that correspond to the u component of the velocity, and the rows that correspond to the W position of the velocity. So these indices are going to be used later in the code to quickly extract that part of the state that we want. Do we want the position of the Lagrangian particles? Do we want the U velocity, the W velocity, or the sea surface height? We can reference those using these indices. Another thing to note is that I have 3 pointers, 1, 2, and 3, and that's because the way we are going to time integrate the model is using what's called a leapfrog scheme. And so that means that we save at any one time 3 state vectors, 1 for the previous time, 1 for the current time, and 1 where we're going to store the newly computed state. So what we do is, it's called a leapfrog scheme, and we take the state of the model at a previous time, we use the current time to compute the time rate of change of the state, and then we time step going from here to the future time using the time tendency computed at the midpoint between now and the future point. So each time step is 2 delta t in length, but after we've done this time step, we then start from here and we do another time step of 2 delta t to leap over the current one. And so that's why it's called the leapfrog scheme. The reason we use this scheme is because it's what's called a symplectic scheme, and it conserves the energy. So if you do just a straightforward Euler forward time stepping scheme, then you will find that the energy of the wave will decay away to 0 with time, even though there's no explicit friction in the model. If you were to do a implicit scheme, I forget which way it goes. Euler forward, maybe the energy grows exponentially and eventually the model blows up, and if you use the Euler backwards, then the energy damps out to 0. Neither of which is correct, because the problem we're trying to solve, they conserve energy, there's no viscosity. And so the leapfrog scheme has the advantage of conserving energy. All right, so all these states here, H gets packed into the state array S for the first slice. We only initialize at one time. The snapshot at P2 and P3 are going to get filled up in as we time step the model forward. But H goes into the IH position, U goes into the IU, W into the IW, and so on for the Lagrangian particles. And then all this gets passed back to the main code for the state, along with these 3 pointers that tell us what's the current time step. And then we also updated the parameter array to include these indices, where to find what inside the state vector. All right, so that was initialize. That's over here. So after we initialize, we're ready to start running the model. And so to prime the pump for this leapfrog time scheme, we first take a 1 delta t time step using an Euler forward time step, and then we're going to use that one to do the leapfrog, and every subsequent step are going to be using the leapfrog scheme. So what is first done is we use model using the current state, S pointer P1, to calculate the time tendency of the state, ds dt, and then we update the model state using just a simple Euler forward for the first time step. We put that inside position P2 in the state array, and then we start doing the while loop, where we integrate the model. So the whole time stepping loop is over here. We're going to run the model for a period of time that's long enough for the wave to cross the basin, right? So the width of the basin is L, the speed of the wave is C. So the wave, the crest that's starting on the left side of the basin, is going to have time to cross the whole basin during the integration. We update the time, calculate the time tendency, and here you see we use the P2 state to leap over the P1 state and end up in the P3 state. So we're always doing this leapfrog scheme. And then after we've done this, we shift the P1, P2, P3 around such that the P1, the oldest state, we're going to override it with the next one, and what used to be the mid state is going to become the old one, and what used to be the new one is going to be the current one. So these just get shifted around cyclically. And every 50 time steps, we're going to make some plots to make the animation that I showed you a little while ago. we can, I guess that's the whole code. What we haven't looked at is how we make the grid and how we make the finite differencing operators. Oh, and how we calculate the time tendency here. So first, let's look at the time tendency. So if I go to model, over here, first extract the density and the gravity, g. We then extract from the state variable the current state that was passed in, the C surface, the free surface, and the velocity vector, v, which has both the u and the w components. And then we are going to, first thing we're going to do at each time step is solve the Laplacian equation to get the pressure. So that's the Laplace operator subject to the pressure at the surface being prescribed to be rho gh, and the bottom boundary condition is that the normal derivative of the pressure has to be 0, and we do that so that the w will always be 0 at the bottom of the basin. So those so that's done over here. We set up a right hand side, and then we invert the Laplacian operator over here using this invert function that got created along with the difference operator. So I'll show you this in a little bit. But after we've solved for the pressure in the interior of the domain, right, we only fill in the pressure in what are called wet points. The dry points are the ghost points I talked about on the blackboard, the ones in the atmosphere and the one in the solid earth. Those ghost points get filled in using the interior points with this operator called BC, which we'll go over in a little bit. So once we have the pressure, we can then compute the time rate of change of the velocity over here, right? dv dt is minus 1 over density times the gradient of the pressure. And that's what this line does. So it's straightforward. We update, we compute dv dt. dh dt is also easy to compute. It's just w, which we have from the current model state. So once we have dh dt and dv dt, we then need to compute the time rate of change of the position vectors for the particles, and that is just u and w. There's an extra step in that because the mesh is staggered, the w and the u points are at different places in the grid, so we have to interpolate them onto the position of the particles. So this is done over here. We take the u and the w and we use MATLAB's 2D interpolation function to interpolate the 2D array of u components of velocity at each position for all the Lagrangian particles. And similarly, we interpolate the w velocities to the same positions to get the dx dt and the dz dt. And then these time tendencies are all packed into this one state vector, dh dt, dv dt, dx dt, and dz dt. And then this is what is then used to time step the model forward. All right, so I guess the next routines we haven't looked at is how to make the grid. And so that's the same grid I described in the blackboard. Here at z equals 0, we have the C surface, and there is this row of ghost points above that are used to compute w at the surface. And then we also have a row of ghost points at the bottom, again, to set w to be 0 at the bottom. And I'll show you how we fill in these rows of ghost points using that BC operator I talked about before. But anyways, the mesh is like that. It's pretty straightforward. The W's and the U's are at the interfaces of the boxes, and the P's, the pressures, are in the center. We also have a mask of zeros and 1. Zeros indicating ghost points or land points, and the ones being wet points. So in principle, we could change the mask. For example, I was experimenting here where we can zero out parts of the domain to make like a seamount, and we have the waves propagating at the surface and interacting with the seamounts. But for right now, we just have a flat bottom. So the only dry points, I guess, or ghost points, are the layer in the atmosphere and the layer in the solid earth. So that's the bottom and the top over here. We also pick out the row of points that are just of pressure points that are just below the surface, and those will be used to prescribe the surface boundary condition that P is equal to rho GH at the surface. And so we find those by setting the row of P points just below the C surface, setting it to 1 in this mask, this surf mask, and then we find those indices. and then everything is packed into this GRD array, this grid array. Using that, we can compute the operators, which are done, as I've demonstrated before, using these permutation matrices built up from the identity to get the points to the east, to the west, above and below. And then we can form a d by dx by doing the point to the east minus the current point divided by dx, and a d by dz by the point above minus the current point divided by dz. And then the gradient is built up by just stacking these two block matrices one above the other. So you're taking the pressure field, for example, and you'll return dp dx and dp dz with this array. And then the divergence is straightforward. It's just obtained from minus the transpose of the gradient. And once we have the divergence of the gradient, we compute the Laplacian operator as div.grad, or in matrix form, divergence times the gradient matrix. All right, so the really tricky part is this business of doing the boundary conditions. And so over here, we have these arrays, BI, BC top, BC bot, and BCE, BCW. And they are arrays that they're diagonal matrices with ones and zeros. So BI has ones on the rows, on the diagonal row. They are on the diagonal points, 4 rows corresponding to interior or wet points, we set a 1. So this array here will find all the P points, pressure points that are in the interior of the domain. And then BC top is going to find all the points, or BC bot, I mean, are going to find all the points that are dry, that happen to be just below a wet-dry boundary. So just below the surface, just below the water in the land. And so this is done by just taking a finite difference of the mass point. So if you're just below the land, the interface between the land and the water, then if you do a finite difference doing the point above minus the current point of the mask, you'll get a 1 minus a 0, it'll give you 1. And so this happens only at the points just below the bottom bathymetry. So BC bot finds all these points that are just below the surface, not the surface, just below the interface between the land and the ocean at the bottom. And BC top does the same thing, but the point just above the ocean in the atmosphere. So this is done by looking down. If you go down and you have a 1, and above you you have a 0, then you must be at the interface between the air and the water. And then BCE and BCW, they do the same thing. If there was a seamount, for example, if you're going from a wet to dry or dry to wet, it'll find those boundaries. And then we use those matrices to fill in the missing points that we will need to compute gradients later on. So, for example, the interior points just get copied in, but if we're at the bottom, then we will just copy the pressure, the value of the pressure in the point just above, below, and that will ensure that the pressure has the same value at both places, so that when we take the finite difference of the pressure, we'll get 0, so that dPdz will be 0 at the bottom. And that is what we need if we don't want any W component, so no velocity flowing into the land. And so that's what this one does. This is the same thing for the top, but now the boundary condition at the top is not that W is 0, it is that P is prescribed to a certain value. So what we do is we extrapolate using 2 points in the ocean up to the ghost point in the atmosphere. So we do that by taking 2 times the current point minus the point below, and that gets shifted up into the ghost point in the atmosphere. And that way, when we take when we apply the boundary condition to the Laplacian, we can ensure that we can average those 2 pressure, the ghost and the one just below the surface, average them and make sure that they're equal to rho GH. And you'll see that in a little bit. And these are similar to the one we had in the bottom, making sure that du dx is 0 at the wet-dry interface, and Here again, du dx is 0 at an eastern boundary, at a western boundary. So there's no flow into the seamounts if we had one. So these last two are not going to do anything for the present model because we just have a flat bottom. All right, and now we're going to use these boundary condition on the Laplacian operator. So first thing we do is we identify the surface points, and we zero out all those equations corresponding to surface points, and then we replace them instead by an average of the current point and the point above. And remember, the point above is a ghost point that we've filled in by extrapolating. And so that average will be set to rho gh in the when we invert the Laplacian operator. And then so now the way the del 2 operator works is we take the pressure, we use this BC matrix operator that we create over here to fill in all the ghost points, and then we apply the Laplacian, and this is our new Laplacian operator. We only solve the Laplacian for the wet points, so after we've constructed our operator that we want, we strip out all the land points. So we retain only the rows that correspond to wet points and only the columns that correspond to wet points. And then we pre-factor the del 2 operator so that it's easy to invert it. So basically this does the Gaussian elimination you would need to solve the n equations and n unknowns to solve Laplace's equation on this finite difference mesh. So this factored matrix gets put in here in a routine I called invert. So invert basically solves Laplace's equation subject to the prescribed boundary condition. So you put in the right hand side, and out comes out the pressure field at all the wet points. All right, I think that's the whole code. So we can now give it a whirl again. So let's run it one more time with the regular wave, and then we'll change the wavelength. So water wave 1. There we go. So you can see the particles at the surface. Once you reach the surface, they're moving horizontal, and then just when you're at the inflection point between a crest and a trough, it's pointing straight down. And then when the wave is rising, you can see it moving up along with the wave. And you can see how they kind of decay with depth. I'm going to pick a shorter wave, and you will see that they will decay more quickly with depth. Right? It goes like the hyperbolic cosine of k times h. And let's stop it. Close all, clear all, and let's change the wavelength. So lambda, let's make it 600. No, that's longer, so let's make it 150. Yeah, how about 50? Make it a very short wavelength. So we should have a shorter wave now. Oh, all my points are all in one part of the domain. But now you can see the top one making circles, but the lower ones are already decayed, so you don't see anything happening down there. Maybe that was a bit too short of a wavelength. Okay, let's stop it here. Let me pick a longer wavelength. 50, let's pick 100. Now we should be able to see the second row moving around a little bit. You can see a little bit of motion, but very quickly it damps out with depth. So if you have long wavelengths, the effects of the pressure can penetrate deeper. If you have very short ripples, the pressure anomalies don't extend very deep down in the ocean. So, if you're a submariner, you want to be below, if the typical wavelength, depending on the typical wavelength of this swell, you want your submarine to be parked below the depth at which these waves propagate down. That way you won't be seasick. Whereas if you're a ship on the surface, you'll feel all these waves. All right, let's try an even longer wavelength. So the original one was 200, I think. What did I have? Grid.dx times 200. No, times 300. Oops. Yeah, 300 is 1,000, so let's pick 600. That will be 2,000. No, let's have one wavelength. It's 900, right? 900 star grid.dx. Yeah, so now we have just one wave across the whole basin. So that's as long as we can fit in our domain. Clear all, CLF. And we should see the wave penetrate much more to the bottom. In fact, it might even start feeling some of the bottom. You see that the circles get distorted because of the bottom. They can't go through the bottom, and they become more like ellipses. And so the wave orbits get squished. All right, so now I modified the water wave 1 to change the initial condition, basically. So all the other parameters are the same. The only thing I did is, instead of initializing with a wave that's propagating eastward, I have a fluid that's at rest, but with a hump of water in the middle of the domain. So it's as if somehow you managed to pile up a whole bunch of water, and then you let it go. And so gravity is going to pull it down, and it will oscillate and produce a bunch of waves that radiate away. So the initial conditions, let's look at the initialize. Where is it? Here. What I've done is, here it is. So H is a form of a bell-shaped curve, like a Gaussian, centered at the midpoint of the domain, and the standard deviation, or the width of it, is 1/300th of the width of the domain, L. So it's a little hump in the middle. The amplitude I picked, I can't remember. Amplitude, let's see, what is it? Amplitude is 100 meters. So 100 meters high, it's pretty high. L divided by 300 is about 100 meters. So maybe it's as if a meteorite just crashed into the ocean and created a mound of water. All right, so let's try this version of the code. All right, so this is an example where you do see dispersion, hence the word dispersion relationship, is that initially you have a bunch of waves that are superimposed in such a way to construct that Gaussian hump, so they interfere just perfectly to cancel all the velocities and to produce that shape at the free surface. And then when you let it go, then all the waves propagate at their own speeds, and so they all disperse, and you end up with a bunch of ripples. And all this perfect interference that cancel the velocities goes away, so they don't cancel perfectly, and then you get a whole bunch of motion associated with these ripples that are moving out. And so there's going to be this concept called the group velocity, which is the speed at which the packet of waves moves, and that's the speed at which the energy moves, which is different than the speed of all the phases or the crests and troughs move. And that's why if you try to keep your eye on a crest, they seem to appear in the back, grow and decay and disappear in the front. And that's because the packet is moving more slowly than individual crests within the packet. All right, so that was the demonstration of the finite difference water wave code. And I will post it to the course website, and you could download it and play with it if you like.